Hello again, this is our example 17. It's a Taylor polynomial for log of x at the base point a equal to 1. So just for notation, let's just call the function f, and then evaluating the function at 1, I get log of 1, which is 0. Taking the derivative of log is 1 over, so I have 1 over x. And I'm going to think about it as x to the minus 1, so I can take further derivatives. But before doing that, if I evaluate the derivative at the base point, which is 1, I get 1. And so the first order Taylor polynomial, just a linear approximation, is going to be 0 plus 1 times x minus 1. This should make some sense. It is the linear function that best approximates log of x near x equal to 1. Let's continue to get the fourth order approximation for this function. The second derivative is minus 1x to the minus 2. The third is minus 2 times minus 1 is 2x to the minus 3. The fourth is minus 3 times 2 is minus 6 times x to the minus 4th. So when I evaluate the second derivative at 1, I get minus 1, and dividing by 2 factorial, which is 2, I get minus a half. Evaluating the third derivative at 1, I get 2, and dividing by 6, I get 1/3. And evaluating the fourth derivative at 1, I get minus 6. Dividing by 4 factorial, or 1 over 24, gives minus 1/4. So here's what we're finding for log of x based at x equal to 1 or a equal to 1. We got 0 plus 1 times x minus 1, minus 1/2 x minus 1 squared, plus 1/3 x minus 1 cubed, and then finally minus 1/4 x minus 1 to the 4th is the fourth order Taylor polynomial based at a equal to 1. Let's just check that the derivatives agree. If I evaluate this right-hand side at x equal to 1, this is 0, 0, 0, 0, 0. Everything is 0, I get 0. I take the first derivative, then here I will get 1, and here I will get minus 1 times x minus 1. Here I'll get 1 times x minus 1 squared. Here I'll get minus 1 times x minus 1 cubed. Anyway, everything will vanish when I put in x equal to 1, except for this first term, and that's the derivative. Okay, let's take the second derivative. This disappears. This is linear, so its second derivative is 0. Here when I differentiate once, I get minus 2. When I differentiate again, I just get that. So I have minus 1 over here, and then when I differentiate this twice, I'll get 6x minus 1, and 6 over 3 is 2, but there's an x minus 1 in there, and when I differentiate this twice, I will get 12x minus 1 squared, and so that will be minus 3x minus 1 squared. Putting in a equal to 1, I'm going to get minus 1 here, 0, 0. So that's minus 1. For the second derivative, differentiating 3 times, the first 3 terms all vanish. Over here, I get 3 times x minus 1 squared, and then 2x minus 1, and then the third derivative will just be 1. So I'll have 3 times 2 times 1 over 3, which is 2. And when I evaluate that at 1, I'll get 2 because it's a constant. When I differentiate this 3 times, I'll get 4 times x minus 1 cubed times 3x minus 1 squared times 2x minus 1. There'll be an x minus 1 here, and when I evaluate it a equal to 1, I'm going to get 0. And so the third derivative really is 2 coming from this term. Finally, the fourth derivative, all of these will vanish. When I differentiate this 4 times, I will get 4 times 3 times 2 times 1, which is 24. And 24 over 4 is 6, so I have minus 6, and that's the derivative that we had. In other words, we're just making sure that we understand why we took the derivative and divided by 2 factorial, 3 factorial, 4 factorial.